Yeah, hello everybody. So I want to welcome all of you here in the Moscow State University. So in this our new summer school on radiochemistry. So it's in the field of decommissioning, and I hope that it will be fruitful and interesting for you. And and especially my welcome words to our guys who was here last time in our last schools and the new participants, of course, also. So, and I want to take the floor to Vladimir Petrov. He will tell a few words about Moscow State University.
Yeah, thank you, Andrei. So welcome everybody. Just maybe a few words technical, because I think for most of us the place is new, and so we will have not only scientific program but also lunches, coffee breaks. Coffee breaks, as you can see already, will be here in this room. Lunch will be in other building. My colleagues will show you. You will follow them to this place, and we will have special tickets, yeah, for lunch. So with these tickets, you will go to canteen, and you will have food for 400 rubles. Usually it's enough to have a normal lunch. What else? We have rooms for ladies and gentlemen on the second floor and on the first floor, just on the right side from the stairs. And today we will have a welcome dinner at a Russian restaurant called Durdin. It's not far away from here, just 10 minutes maybe by walk. So we will go there by walk, so not far away. And we will have our program will continue till the Wednesday next week, so 27th of August. During these days, we will have lectures. We will have tomorrow and the day after tomorrow two practical tours. They will be about the decontamination of the surfaces, and more information will be again tomorrow. And we will have different activities also for you as excursion tour guided through Moscow and some other activities. So just some information about our school, how it will be during these 10 days. I hope it will be not very useful, but also very nice for you. And now we have not very hot weather. That is also nice for us, at least. Yeah. It's not very cold, but it's not very hot. I think it's very good weather for walking around. Just a few words about our Moscow State University. So our team that organized this school with the support of the Rosatom. We are a team of me, Vladimir Petrov, Andrei Putyatin, Yulia, Kirill, Anastasia, and Timofey, Svetlana. We will help you to spend this time. Olga, somewhere there. Everybody knows Olga, yeah, already. So we will help you to have a good time during your stay here. So our university is the oldest university in Russia. It was established in 1755 by Lomonosov. And today it is the largest university. It's more than 40,000 students. One of the department, so we have, as far as we university, we have quite a lot of different departments from the social sciences, so some humanitarians, some psychology, even TV program, and we have natural sciences, chemical, biology, chemistry, physics, nuclear physics, and what else we have? We have space studies, economy. So every field of the knowledge of the humankind, I think we have in our university. And one of these 50 departments is the Department of Chemistry. We have around 18 divisions. One of the division is the division of radiochemistry, where we now, and so this separated building, it is only for our division of radiochemistry. Our division consists of 7 labs. So it is laboratory of radionuclides and labeled compounds. So they're mainly working with the labeling of organic compounds for biochemical and other studies. It is a laboratory of heterogeneous processes. They are studying the process on the, let's say, border of the two phases, like the solid phase and liquid phase, to see the process of the crystallization of the compounds. It is laboratory of nuclear chemical methods of analysis and Miss-Bauer laboratory. Now these two laboratories are joined together, and now it is one laboratory of Miss-Bauer spectroscopy. It is a laboratory of dosimetry and environmental radioactivity. I am the head of this laboratory. It is laboratory we have 3, even 3 quite new laboratories. They're like 5 to 10 years old. It is laboratory of radiopharmaceutical chemistry. It is laboratory of chemical physics of F elements, and our inter-divisional laboratory of smart chemical design. It is now it is a laboratory, separated laboratory, but previously it was a group of people who worked in our laboratory of dosimetry, but with the development of the methods of the quantum chemistry and artificial intelligence, they now are so big, a big group of people that they already separated as their own laboratory. We have abilities to work with the quite large amount of radionuclides. So we have a license, state license, to work with the up to 15 gram of plutonium. We can handle. We don't have 15 gram of plutonium, but we can. We may work. We are allowed to work with such amount of radionuclides. We have quite a lot of different radioanalytical techniques, and not only radioanalytical techniques. We have ICP-MS for radioactive samples. We have transmission electron microscopy with high resolution. We have X-ray photoelectron spectroscopy, and we have quite a good collaboration with Kurchatov Institute, where our at the moment the only synchrotron source in Russia is located, and there is a radiochemistry station, a radiochemical station at this Kurchatov Institute synchrotron, where we can also measure our samples. And today, with the development, with the foundation of the Laboratory of Chemical Physics of F elements, today we have our lab size X-ray spectrometer, which we can use also for XANES and EXAFS measurements. And the head of our division is Professor Stepan Kalmakov, who is now academician and also vice president of the Russian Academy of Sciences. Even at this very top position, he still makes quite a lot of scientific work with the PhD students, with students, with us. He's very clever guy, I would say. So what we have also, we have an agreement with International Atomic Energy Agency on educational and training programs. Recently, we joined the Almera network for radioanalytical lab network, and this summer it was we were added to this list of the radioanalytical lab within the Almera network. We have, as I mentioned already, we have a state license to work with radioactive materials for research purposes. So we, of course, we cannot make some industrial scale experiments, but we can do it for research purposes. Also, we have a vivarium here, so we can work with the mice and rats to investigate these new radiopharmaceuticals and new medicine for with the use of radionuclides. So this not the full list of the radionuclides that we can use in our research work, but maybe some more interesting radionuclides. But actually, the full list is much longer. So if you may be interested to work with some unusual radionuclides, we can do it, and it also can be in future as a collaboration with your institute or center. What I mentioned before, this lab scale X-ray spectrometer that we can use for XANES and EXAFS experiments. Later it will be one of the lecture about these methods, and I hope that we will show some examples how we can use it. Today we have 3 master programs, English language master programs for Russian and foreign students. It is our first master program is project management in the field of decommissioning of nuclear facilities, including radioactive waste management. The second master program is master in radiopharmaceutical chemistry, and the third master program is the master in spent nuclear fuel management. So it is already launched. And every year we have at least two international schools, summer schools as now, and winter schools. This year it will be in November, so it will be not so warm already. So maybe already will be some snow. But it's still a very nice period of time and a very nice opportunity to know something new and to exchange your experience with other expert students, specialists. We have 25 students for each school annually, so it is more than I think it is already more than 20 countries that we have already. So because it is more than 20, not 20, it is more than 10 schools that we already have in our radiochemistry division. So quite a lot of participants already have been here. And it is, as I mentioned, not only scientific schedule, not only scientific classes, but also some informal communication, some informal events, and I think it will be quite good also this time. There are a lot of different topics during these schools that we already given these classes, these lectures and seminars. This school, as you already know, it is devoted to the decommissioning of nuclear facilities, and we will look through the some technical details of the decommissioning, some regulatory questions of the decommissioning. We will see some experience from different countries of the decommissioning, and we will see on the related, we will look on the related topics like the characterization of radioactive waste that arise during the decommissioning activities. So going more deeply in details about our expertise, about the expertise of the division of radiochemistry. We are working quite a lot of on radioecology. Today, quite a lot of on geological disposal of radioactive waste. It is development of different techniques for water purification and remediation of the contaminated territories. It is, of course, nuclear medicine, including production of the radionuclides for medical purposes. It is separation chemistry, material science, quantum chemical calculation, and artificial intelligence also, methods for chemistry, for radiochemistry, and synthesis and investigation of the labeled organic molecules, organic matter. So about the just few words about each of the direction. Radiopharmaceuticals, we are working with all the not the all the cycle, because we cannot do the clinical treatment, of course, clinical testing of the radiopharmaceuticals, but we are starting from the production of radionuclides. So we develop, my colleagues are developing schemes for the chemical separation and purification of the radionuclides that can be produced either in reactors or on with use of the accelerators. Then we, after the extraction and purification of the radionuclide, we can investigate its properties. It is stability constant of the different complexes. It is stability of these complexes in vitro. So it is the biological, let's say, or close to biological environments. It is investigation of the best methodics for the synthesis of the radiopharmaceutical. And as I mentioned, we have vivarium, so we can investigate the distribution of radiopharmaceutical and their evolution, let's say, in organism of the rats and mice here at our division. Extraction studies or separation studies, today it is not related not only to radioanalytical purposes, not only to the production of the medical radionuclides, but today we work quite a lot on the methods for the reprocessing of the spent nuclear fuel, with the further development of the methods for the fractionation of the components of the spent nuclear fuel. It will be another part of another lecture, but just a few words, because nowadays the only technological industrial method for the reprocessing of spent nuclear fuel, it is Purex process, where we separate uranium and plutonium, and all the rest goes to the high-level waste for the disposal. But today, with the development of the closed nuclear fuel cycle, we have to extract, to separate also the long-lived radionuclides like americium, for example, neptunium, and some other components. But the most difficult part of this separation is the separation of the pure americium, because there are lanthanides also in spent nuclear fuel. There is curium. All these elements, they have very close chemical properties, and we are investigating, and we have developed the method for the separation of the americium with the use of the liquid extraction. And another example is the fundamental studies of this extraction processes. One of the, I think, very interesting example is the study of the very well-known element uranium. So uranium extraction of uranium investigated since 1940s. So already, let's say, 80 years, more than 80 years. But still, with the use of the synchrotron methods, with the use of different techniques, it was for the first time shown that there are some extractant, some molecules, tetradentate ligands, with the nitrogen atoms as hetero atoms, that can form complexes with uranium where two uranium are located in the same, let's say, complex. And uranium existed both in cationic form and in anionic form simultaneously in this complex. So it was published recently, just 2 years ago, by our group, by a group of our colleagues. So it was quite interesting results, some fundamental new discoveries, even for very well-known systems. Also, with the help of the quantum chemistry, today we can at least estimate the stability of organic molecules, so their resistance towards radiolysis. So again, a group of my colleagues from this new laboratory of the smart chemical design, they developed a quantum chemical model to predict the radiation stability of different organic molecules. And today we are developing this model. We are planning to use not only quantum chemical modeling, but also the help of the neural network computation to predict faster, at least, this radiation stability of organic molecules. Because the quantum chemical calculations, they are good, but they require quite a lot of time. So, but with the let's say, with the construction of the database with enough data, later we will be able to use the neural networks to predict the stability of these organic molecules. What else we are doing, especially with the focus on the disposal or storages for radioactive waste, It is investigation of the properties of the engineered barriers. So on next Tuesday, it will be a lecture about barrier materials. So my colleague Anna Semenko will give you some details about our studies. So mainly it is clay materials, clay-based materials, or plus cement materials that play a role of the engineered barriers to prevent radionuclides to be released in the environment, or if there is some failures in the barrier systems, the properties of these materials are focused on the sorption of the radionuclides to prevent the further release in the environment. So, and a group of our colleagues, they are working on the investigating of the fundamentals of these properties of the engineered barriers to have some, let's say, algorithm, I would say, to choose or to select the materials that will have the best properties for the certain repository or for the certain storages, based on the geological environment, based on the chemical properties of the radionuclides that have to be stored in this place, in this site. So it will be the final idea, the final aim is to have such algorithm or advices for people who construct repositories, how to choose correctly the materials, materials for these engineered barriers. Another topic is again fundamental properties, fundamental aspects of the sorption processes on the engineered barriers, on the natural minerals in the environment. So the thermodynamic modeling, thermodynamic, how to say, the analysis and the measurement of the thermodynamic parameters of the sorption properties of the radionuclides with the different materials, natural materials or artificial materials. With the use of these thermodynamic parameters, we can model the process of the sorption of the radionuclides and predict the sorption behavior in different environments. Thermodynamic modeling is much better or much more powerful than conventional approach with the use of the distribution ratio, because distribution ratio can be determined only in specific conditions, and it cannot be used in other conditions. For example, if you increase temperature or increase salinity, distribution ratios will be different. But the thermodynamic parameters, they're universal, they're constants. Yeah? So you can use them in any conditions. You can calculate the behavior of radionuclides if you know thermodynamic parameters. Another topic, again related to investigation either of the radionuclide migration or in the environment, or radionuclide behavior in technogenic, let's say, environment after the accidents. It is characterization of the materials with all the methods that we can use: scanning electron microscopy, mass spectrometry, XANAS, EXAFS analysis, to see what the evolution of the materials with the time. So we have samples from the Chernobyl lava. We have samples from the we have environmental samples from the contaminated areas, so we can analyze what is the fate of the radionuclides in these objects. Thus, we can use this information to predict, or let's say to make a safety assessments for the radioactive waste repositories. And again, the modeling of the thermodynamic modeling, not only the sorption of the radionuclides, but also, let's say, the fundamental chemical properties of the radionuclides or their particles. It is dissolution of the particles, or colloidal particles, or bulk samples. It is hydrolysis, it is complex formation, and many, many other investigation. It is, again, interaction of the radionuclides with the real rock samples from the future high-level waste repository site, so we can investigate how different minerals are responsible for the sorption, sorption of different radionuclides, specific plutonium, cesium, strontium, radium, americium, neptunium, whatever. And we also develop algorithm or method to estimate the differences in the sorption activity of different minerals that are present in one natural rock sample. So we don't need to separate each mineral grain by grain, but we can just take a bulk sample of the natural rock. We can sorp our radionuclide of interest, and then we can quantitatively estimate the difference in the sorption activity of different minerals towards the specific radionuclide. Then, with the use of all these thermodynamic modeling, thermodynamic parameters, we, of course, cannot avoid the analysis of natural samples from the contaminated territory or affected territory. For example, territory where was former mining of different minerals, including thorium-containing minerals, so we can estimate how thorium is released from these mines, and to see the migration behavior of thorium that is analog for other actinides. So, to combination of all these experiments and data from the natural samples, data from the lab experiments, final aim, final objective is to build the model of the migration of the radionuclide in the specific environment, to be able to make a safety assessment for future either high-level waste repository or intermediate level waste repository, or any other storage facility. And of course, one of the important part of the decommissioning or radioactive waste treatment management, it is the monitoring of the environment around these storages and repositories. And this environmental monitoring include not only just measuring the dose rate or measuring the gamma radionuclide in soil, but it is also samples of air, water, animals, plants, whatever. All the components of the environment must be controlled, and this we can also do in our laboratory. So just few examples. So that is main let's say fields of our expertise, what we are doing in division of radiochemistry. And again, I'm glad to welcome all of you here, and I hope that this week we will have a lot of good conversation and good time. So thank you. So now, as you saw in our schedule, we will have just a short testing of you. So again, for those people who are not the first time here, I remind that it is nothing with the estimation of your personal skills. It is just for us to know, to compare, let's say, the level of expertise of people before school, and then it will be final testing to see was this level improved or stay the same. I hope it will be not decline. So again, the only thing I will ask you to write your name and surname. This is not again for evaluating your personal skills. It is for us for formal parts that all the people who must be here, they were here, and we can prove to our colleagues from Rosatom that everybody have been here. Okay, so Slana, can you give these sheets? So there are 2 pages, so don't forget to fill both pages, and we will have quite a lot of time. So when as far as we're quite flexible here, when all of you will finish the testing, we can continue with the next lecture. Okay, we will have a short break, of course, and then we will continue with the next lecture. Okay, so now it's okay. So and should present it. No, sure. So and we'll start with just again general information about the nuclear energy and energy at all. So today, as probably many of you know already, the situation with the energy not the perfect. We still need quite a lot of energy, even in the developed countries, and you know that there are more and more power stations are under construction, and a lot of nuclear power station, of course. So today we still have around 1 billion people with the no excess in energy or to poor access to energy, and still more than 2.5 billion people they rely on biomass. This, according to the World Health Organization, leads to poor situation with the medical care, with the health care. So 1 billion people have no health care or very limited access to healthcare, and due to the use of the biomass with the use of the uh, fossil fuels, there are excess of 2 million deaths per year due to the contamination of the indoor air, due to the contamination of the environmental air. And today still the main source of energy is the fossil fuels. We burn coal, gas, use oil, heavy fractions of oil. And according to International Atomic Energy Agency, if we want to reach the climate goals that we want to reach, we want to meet, that means that till the 2050 year, we need to have more than 80% of electricity that is generated by low carbon sources of energy. Today it is less than 30%. So it's a very ambitious goal. And if we are choosing among the cleanest or sources of energy or sources of energy with the lowest carbon emission, there are two main sources. It is hydropower, nuclear energy, wind and solar energy. It is in publications, in articles, in media, there are always like debates or competitions between the wind and nuclear energy, what source of the energy is the lowest in the carbon emissions. So they go really close to each other, wind and nuclear energy. And in this chart, these emissions, they are calculated, taken into account all the steps in the production of energy, including the building of the construction of the buildings for the power stations. For example, we don't use the fossil fuels in nuclear energy at all, but still there are CO2 emissions due to the use of the trucks, construction with the cement, etc., etc. So there are still CO2 emissions, but of course with the lowest amount among other sources like coal and oil. And what is even maybe more surprising, that these four sources of energy, they are also the safest sources of energy in terms of the death rate from the accidents and air pollution by different sources of energy. So here the numbers of deaths per 1 terawatt hour of the produced energy. And it is not really surprising if we analyze again the news, for example, in media, where we can quite not very often, fortunately, but still, I think everybody of you remember some news, maybe in your country or in other country, when some coal mines collapsed, and there are accidents in these coal mines, for example, that lead to the deaths of the workers, these accidents. And fortunately, we don't hear such news from the nuclear energy. So the last was in Fukushima, more than 10 years ago already, almost 15 years ago. So, and still there were no death from the ionizing radiation, but due to the water flooding and the fire on the station. So if we calculate, if we will see on these numbers, we will see that again these four sources of energy, they are the lowest in carbon emission or greenhouse gas emission, and they are safest, so they are lowest in the death rates from the accidents and air pollution. So it seems that it is a very bright future, I would say, for these sources of energy. Why me personally, I'm for nuclear power plants, not only because I'm working with radioactive materials and in working in this field, but also because nuclear source of energy, it is the most concentrated source of energy, because energy produced by the release of the atomic power or nuclear power, it is from, let's say, 5-6 orders of magnitudes more concentrated than any energy that we can produce by chemical reactions. That's why if we compare the energy that is released from the 26 cubic meter of the natural gas, it is one of the best source of energy from the among the fossil fuels. We will need only 26 milliliters of the nuclear fuel to produce the same amount of energy. So it is 1 million times difference in the volume of the fuel that is required for the production of the same amount of energy. So also, if we will look on the wind or solar power, we will see that the area that is required to produce the same amount of electricity will be much larger in comparison with the nuclear power plants. So it is, let's say, 100 and 300 times more area that is needed to put all these solar panels and wind turbines to produce the same amount of energy. So it is, again, the use of nuclear power plant, nuclear energy leads to the more more efficient use of land, let's say. So together, these four types of these four sources of energy, they combine in so-called green square or green quadrant. These two sources, nuclear power plant and hydro power stations, they are like a basis for the square, because they can produce constantly the same amount of energy. So they have constant power production of energy. And for the peak needs of the electricity, of energy, these two sources, wind and solar power plants, can be also used to how to say, to accompany these main types of the energy. Also, again, the nuclear power plant and hydropower stations, they can produce very high uh, high currents and that are important for the industrial applications, for the plants that produce metals, for example, which requires quite a lot of energy and very big powers. So nuclear energy from different points of view is one of the best options to produce energy. It is one of the cleanest and safest sources of energy. Also, the nuclear energy can produce so-called sustainable source of energy because the typical time of operation of the nuclear power plants, nowadays it is a minimum 50 years, usually it is longer. So for more than 50 years, maybe 75 years, you have a great source of energy with the very slow variation in the cost of the energy production, because the main cost of the energy that is produced by nuclear power plants, it is the cost of the construction of the nuclear power plant. The cost of the fuel itself, it's something like 10% of the total cost of the energy production. Thus, if you know the cost of the construction of the nuclear power plants, you know the cost of the uranium or uranium fuel. Nowadays, you can predict the cost of the energy produced by nuclear plants for 50 and even more years. So that makes the nuclear energy sustainable. That means that for very long period of time, with very high accuracy, you can predict the cost of the energy. That is very important for the economics, because if you know the cost of the production of energy, then you can estimate the cost of the production of all the other products, including metals, I don't know, water purification systems, and many others. Of course, there will be difference in inflation, the cost of the people, salaries, etc. But let's say fundamental cost of the production. So you already have the station, the variation of the cost. Even if you have increase in uranium cost twice, that means that the cost of the energy production will increase only by 10%, because the fuel will cost only 10% of the total cost of the energy. So that means that even the high variation in the cost of the uranium and the nuclear fuel will not significantly affect on the total cost of the energy production by nuclear power plant. And it is not the same for gas or oil station, because in this case, the cost of the production of the construction of the power plant is not so high, and more than 70% of the total cost of energy comes from the cost of the fuel. And in this case, if you have very large variations in the cost of the oil or gas, you will have very high variations in the cost of the energy. So nuclear power plants, they really can produce or provide very sustainable source of energy with known or at least understandable formation of the cost of the energy, and they will work more than 50, or today it is already more than 70 years. So again, from many points of view, nuclear power plants, they are a good source of energy, maybe best, I would say. But again, we as specialists have to build this public trust in nuclear energy, because of course we know Chernobyl accident, now Fukushima accident, there are some other accidents that are not so known among the public, but we as specialists know about them. And it is very difficult to show people that the real numbers, because even in the report of the United Nations organization, the total number of people who died from the direct impact of ionizing radiation today is not more than 200 people. Yeah, but people who heard about the Chernobyl and Fukushima accidents thought that they're thinking that it is more than, I don't know, 100,000 people. So it is difficult to argue with people who don't know the numbers. So our aim also to bring the correct information, but also today especially one of the I believe that one of our main goal to how to build the trust of the public is also to show our experience, our competences in the treatment or management of radioactive waste and spent nuclear fuel, and to demonstrate that we can safely decommission all these nuclear facilities that are, many of them are already more than 50 years old. So it is time to really think about the decommissioning, about the safe decommission of these facilities. Not only nuclear power plants, we will go briefly through the whole nuclear fuel cycle, but also other nuclear facilities, including the plants for the reprocessing of spent nuclear fuel that are already more than 60 years old. And they are the objects where a lot of highly radioactive materials are located and produced every year. So nowadays we really starting to face all these problems with the old objects, and we need to think about the decommissioning already and already start to decommission all these objects. And when we are speaking about the nuclear power plants, nuclear energy in general, we know that last year it was the 70th anniversary when the first industrial nuclear power plant was launched. So it was in USSR, in Obninsk, so not far away from here, so something like 100 kilometers from Moscow. It was the first very small nuclear power plant. It was only 5 megawatt in electric energy, but it was the first nuclear reactor, nuclear power plant that was connected to the electrical grid of the city, and which provided the energy to the city. Of course, today this reactor doesn't work anymore. It is a museum nowadays on the territory of the Physical Energy Institute in Obninsk. And today we are already speaking about the generation 4 of the reactors. Of course, all this classification of the reactors by generations, they're conventional, so it is not like a strict number of parameters when we can say that this reactor is a number 3 generation and this number 4. It is evolution of the reactors, and as well as evolution in the animal world. We can not clearly see this transition species between one species and another, but of course they existed. But we can say, but we can distinguish between two different species. Yeah, the same is here. We can say that some of the reactors, they are definitely generation 2, and VVR 1000, for example, is definitely generation 3. But what is the generation 4? it is still open question, and now we say that new types of the reactors like VR 1200, it is like generation 3 plus, so it is not 3 and not 4, so it's some transition type of the reactor. So this classification by generation, it is I would say conventional, yeah. And when we speak about the nuclear energy, first of all, people think about the nuclear power plant itself, yeah, because energy comes from the nuclear power plant, and usually people forget about other nuclear facilities. But normally, when we speak about the nuclear facilities in general, we are talking about the nuclear fuel cycle. So it is all the steps, all the operations that are started from the uranium ore mining, then the extraction of uranium, its refining, and then conversion to uranium hexafluoride for enrichment of uranium by isotope 235. Then it is fabrication of nuclear fuel. So all these steps made at different facilities. So all of these facilities are different. Then it is only at this step we have nuclear power plant with the production of electricity or energy in general. Then the story doesn't end. Yeah, after work at nuclear power plant, nuclear fuel that is now called spent nuclear fuel goes to the special pools near the nuclear power plants or just at nuclear power plants. After few years of storage, spent nuclear fuel goes to the special storages, centralized storages if they existed in the country. It can be either wet storages or dry storages. And then a story again doesn't end. We have either open nuclear fuel cycle when this spent nuclear fuel goes directly for geological disposal, and we forget about it. Not forget, of course, we control environment, but the further operation with spent nuclear fuel are not considered. Okay, nowadays there are discussions that maybe we should put spent nuclear fuel in disposal and make it possible to take it out after, I don't know, 100 or 200 years back for reprocessing again. But the general idea that we dispose spent nuclear fuel in geological media, and it will store there or dispose there forever. So it is open nuclear fuel cycle because we started from uranium mining, we finish with the disposal of spent nuclear fuel, and there is no closing of the nuclear fuel cycle. Yeah, it is open nuclear fuel cycle. Another story, it is a reprocessing of the spent nuclear fuel with the extraction of uranium and plutonium, nowadays only uranium and plutonium mainly, and fabrication of the fresh nuclear fuel, either with only uranium or with the mixture of uranium and plutonium that is called MOX fuel, mixed oxide fuel, and then use again this fuel at the nuclear power plant. So it is the closed nuclear fuel cycle. Not all the countries accept the closed nuclear fuel cycle. There are only few of them. It is Russia, France, China, now India, and that's it. It was a reprocessing of the spent nuclear fuel in Great Britain, but a few years ago they closed the reprocessing of the spent nuclear fuel because from their data it is not economically feasible, so not good from economical point of view to reprocess spent nuclear fuel, and their plant in Sellafield was launched as a commercial reprocessing plant, so they closed it. In the 70s, it was a ban for the reprocessing of spent nuclear fuel in the United States of America, and there are some problems in the Japan facility. So nowadays it is only four countries, maybe South Korea also. So 5 countries, let's say, who can work with the closure of the nuclear fuel cycle, or who are working on the closure of the nuclear fuel cycle. It's, from my point of view, again, it is very interesting because there are quite a lot of countries that have, let's say, ionizing radiation facilities, including accelerators. So I think it is dozens of countries which have such facilities. It is only maybe 10 countries, or around 10 countries, who can build nuclear power plants by their own. And you can see that there are only 5 countries who can reprocess the spent nuclear fuel. So it is, there are different opinions on why it is so. First of all, of course, it is very expensive to reprocess the spent nuclear fuel cycle. The second the second point, that it requires quite a lot of sophisticated techniques and research work on the technologies for the reprocessing of the spent nuclear fuel cycle, and of course a very long story of the handling such materials as spent nuclear fuel, because it is the most dangerous matter in our planet. But we will see later that the spent nuclear fuel is the most dangerous matter when it is released from the nuclear reactor. But with time, it become not so dangerous, due to the decay of the radionuclides. And any of the facility has its own life cycle. It is true not only for nuclear facilities, but as we are talking about nuclear facilities this week, we will talk about their life cycle. Every life cycle started from the planning, from the idea, what we want to build, what we want to obtain from this facility. We choose a site where this facility should be located, and then we started to design the facility, to make all these technological schemes. We estimate the size of the facility. We have all the documentation of the facility. We know detailed information about each point at the facility, and we have also a license to construct the facility. And then we started the construction of the facility. I would say it is the fastest, the shortest period of time, the construction of the facility. And then we commission the facility and start the operation of the facility. And this stage should be the longest stage of the facility, because we built the facility to operate it, not to just for designing it. And then the final stage of any of nuclear facility, it is probably one of the main difference from other facilities, that we must to decommission this facility. And we'll see what type of facilities we have, and what is the decommissioning. So we'll go briefly through the nuclear fuel cycle. we started from the mining of the uranium ore. And again, it is not the universal method for the mining of the uranium ore, depending on the geological properties, the geological parameters of the ore deposit. We can use either carriers, mines, or underground leaching. So carriers, they are, I would say, the worst scenario for the environment, because we have to dig huge holes in the land and excavate a huge amount of the rock, of the ore. After that, all this ore is collected or as such heaps, let's say, and all these heaps, they are treated with the sulfuric acid to dissolve uranium. Then there is extraction of the uranium, purification, and the final product, this uranium oxide or ammonium diuranate, depending on the technological scheme. Another story with the mines. It is very specific, also mining, type of mining, because in this case, if we have a very concentrated, let's say, formation of the uranium minerals that we can follow and dig in the shafts to mine this ore, then there is only like a entrance to the land, and all the digging, all the excavation goes underground. But again, it is excavation of the huge amount of ore, and the same leaching of the excavated ore on the daylight surface. Another story is the underground leaching. Unfortunately, it is not always possible to use such a type of mining, but from the, again, ecological point of view, it probably the best option, because in this case there is no excavation of the uranium body. It is just a drilling of the wells through the uranium ore body. What we need that this ore body must be isolated from other environment by the isolating layers, probably formed by clays, as an example. So to prevent our acid solution to be released in the environment. So if we inject the acid solution in these wells, acid goes through the uranium ore body, and then this acid solution with the uranium already in the solution goes out through other wells and goes through the pipelines to the plant, where uranium extracted, separated, refined, etc. So in this case, in the land, we see only the wells and the pipelines that can be removed after all the uranium extracted. When the all uranium is extracted, we just remove all the pipelines, and there is just a pure land. And after 10-15 years, it is recovered with trees and plants, so very fast. Depending on the geological situation, depending on the minerals that are forming the uranium ore body, different solutions can be used. If it is like non-carbonate minerals of uranium, We can use acid solutions, sulfuric acid solutions, maybe with addition of some oxidizers. It can be just air bubbling through the acid solution to oxidize uranium from uranium-4 to uranium-6. And uranium-6 has higher solubility in acid in aqueous solution in general. Or if we have carbonate minerals in uranium body, then we cannot use acid because it will be a lot of carbon dioxide production, a lot of pressure, and some accidents can be. So in this case, we can use sodium carbonate solution for the leaching of uranium because uranium-6 can form water-soluble carbonate complexes. And in this case, it is more or less like action of the acid on uranium. It dissolves and goes in the solution, and we take it out. So again, depending on the geology, we can use either acidic solution or alkaline solution. But as I mentioned, these types of the leaching can be used only when specific geological conditions are present on our site. After mining, either by carriers or by mines or shafts, there are a lot of tails that contains natural radionuclides. With the use of the sulfuric acid, we concentrate radium in these formations. So these tailings, they contain a lot of radium, natural radionuclide, but when it is in concentrated form, it possesses danger for the population. Also, if the isolation layer degraded, these radionuclides can penetrate, can be released in natural waters and can go to the wells of drinking water, so it can affect on the population. So that's why this decommissioning of these tailings is quite urgent task in the areas where they exist. And today, quite a lot of actions. Again, it is a good point that today many countries they take a lot of actions to decommission these tailings. So after extraction of uranium and purification it, we need to convert uranium to uranium hexafluoride. We need uranium hexafluoride because it is a unique compound of uranium that has a very low temperature of the sublimation, so it goes to the gaseous phase without going through the liquid phase, so from the solid to gaseous immediately at a rather low temperature of 56 Celsius degree. To convert uranium from uranium oxide or ammonium diuranate, there are a few more steps. Conversion of uranium to uranium oxide, uranium tetrafluoride, and then to uranium hexafluoride. And at all these facilities, there are storages of the uranium hexafluoride in barrels. It is stored in open air because if there any accident with the barrel in a close room, it will cause much more fatal impacts than in open air, because uranium hexafluoride is easily hydrolyzing compound. So if it meets moisture, it hydrolyzes and produce hydrofluoric acid. That is very toxic for people, and it was several accidents at such facilities in the closed room when these barrels it was failure in the canister, and people died due to the hydrolysis of uranium hexafluoride. So why do we need uranium hexafluoride? Because again, it goes easily to the gaseous state, and we can use uranium hexafluoride in gaseous state to separate two isotopes, uranium-235 and uranium-238. Fluorine is, again, it is very good luck for people because fluorine has only one natural isotope. So there are no other isotopes on the fluorine-19 in nature. So it is a monoisotopic element. That means that there is only two masses that must be separated: uranium-235 plus 6 fluorines and uranium-238 plus 6 fluorines with the same masses. For example, if uranium oxides would be volatile, oxygen has several natural isotopes, stable isotopes, 15, 16, 17, 18, and thus it would be a combination of different masses of uranium, oxygen, all these combinations. And it would be very difficult to separate only light uranium from the heavy uranium. But in the case of fluorine, it is only one isotope, and we need to separate only two masses. That can be done by different techniques. Historically, the first technique was what we call now mass spectrometry. So it was the use of the magnetic field to separate two masses, and large magnets and huge facility. So you can separate two masses by the radius of how these two masses go in the magnetic field. But it requires a huge amount of energy. So by estimation, if we today would use this technique, it would require the same amount of energy. So all the uranium that will be separated by this technique will produce the energy that will consumed by this facility. So it will be a closed cycle only for separation isotopes, but no production of electricity for the practical application. So it requires a huge amount of energy. But at that time, for the very first separation of uranium isotopes, the idea was not to use it as a source of energy, but a source of, but for military use. So it was not so important how much energy it requires. But today we know two main methods. It is gas diffusion method, the penetration of the gaseous uranium hexafluoride through a metallic membrane with a pore diameter of 10 to 100 nanometers. So we apply a high pressure, and the uranium hexafluoride penetrates through the membrane. And of course, the lighter the gas, let's say the smaller the gas, the easier it goes through the membrane. So the gas stream that goes through membrane is enriched with uranium-235. And with the repetition of this process several times, we can obtain the uranium-235 with the required enrichment. Another technique is gas centrifugation. In this case, there is centrifugal forces. It is very high rotation of the centrifuges, several thousand rotations per second. So it is very high gravitational or centrifugal forces. centrifugal fields in the rotors in the vessel. So two elements separated, let's say, by gravitational, I will call them gravitational forces. The heaviest metal or the heaviest compound will go faster to the walls of the vessel, and the light isotope will stay more closer to the center. So these two streams are separated, and they go in different directions through this very long line of the vessels. So it is like countercurrent enrichment of the uranium. So in Russia today we use only gas centrifuges. It is more economically feasible again, and today it is already the 10th generation of these centrifuges. And it is an aerial view of the facility for the enrichment in Russia. So you can see that it is quite a long building, something like 1 kilometer building. And again, all these facilities, they're quite old, and they must be decommissioned in the upcoming years. So after the enrichment, we need to produce the nuclear fuel. And nuclear fuel today, it is mainly uranium dioxide. More than, I think, 90% of all the nuclear fuel is uranium dioxide. It is ceramic tablets with the very small size. It's something like 8 millimeters in diameter, 2-3 centimeters in height. It is because uranium dioxide has not perfect thermal conductivity. So that's why we need to have a small tablets of uranium fuel, so it will not be melted. So if it would be bigger tablet, the temperature in the middle of the pellet would be so high that it will be melted. So thermal conductivity is the crucial parameter for the nuclear fuel in this case. So that's why the diameter of the pellet is around 8 millimeters. And yeah, as I mentioned today, it is mainly uranium dioxide, but already 3 years ago, it was, let's say, milestone in the nuclear energy in Russia, when the full active zone of the reactor at Beloyarsk NPP nuclear power plant, so it's BN 800, was filled with the MOX fuel. MOX fuel, it is mixed oxide fuel of uranium and plutonium, and it can be used both for thermal nuclear reactors if plutonium is of good quality, or today it is used mainly for fast neutron reactors. For some reactors, fuel can be metallic, or it can be alloys of the uranium and some other metals like gallium or aluminium or magnesium. It is some reactors use carbide fuel, and the new type of fuel, it is uranium nitride, or that we called also a dense fuel. So the density of the uranium nitride larger, so I don't remember the exact numbers, but larger than uranium dioxide. Also, uranium nitride has higher, very good thermal conductivity. So we can say that uranium nitride fuel, it is a more dense fuel than uranium dioxide. And in this case, we can use uranium uranium-238 in fast neutron reactors in the form of uranium nitride, because in this case the amount of the neutrons that are formed is enough to sustain the nuclear chain reaction with uranium-238. I mean the fast neutrons. Yeah? It is not possible to use thermal neutrons for the uranium-238, but it is possible to use the fast neutrons for uranium-238. And as far as it is very dense fuel, the number of neutrons is enough to sustain the nuclear chain reaction. There are some research reactors with the liquid fuels. There is, I think, only one reactor that use the aqueous solution of uranium sulfate, but there are several reactors, research reactors that are using molten salts as a nuclear fuel. And today there is a project to build a molten salt reactor, like a pilot scale molten salt reactor in Russia to demonstrate the possibility to transmutate the long-lived radionuclide like americium, curium, neptunium, technetium, maybe iodine, to the short-lived radionuclides or even stable nuclides, as in the case of technetium. And of course, the composite fuel, triso fuel and quatriso fuel, that contains of such a small sphere, so it's around 1 millimeter in diameter. These spheres, they are combined in larger assemblies and used in high temperature reactors, gas-cooled reactors, for example. But during the fuel fabrication, if the uranium dioxide fuel is not very radioactive, we can take this fuel just by hands and nothing will happen. Of course, it is not the case for plutonium fuel or MOX fuel or other plutonium or other actinides containing fuel, but for uranium oxide fuel, we can just take it by our hands. But still, even if we use uranium dioxide, it is not very radioactive. During the production of the fuel, there are fuel with defects, with the cracks, for example, or not the ideal geometrical shape, or it is not a homogeneous distribution of other components like gadolinium, for example, or some other defects. All this fuel is dissolved, and go back to the process of the fabrication of the nuclear fuel. During this operation, there is a formation of the liquid radioactive waste. And as far as at these facilities, normally it is not only one type of fuel that is fabricated. The mixture of all these solutions become quite complex, sometimes with the use of nitrites, and it is a very saline solution with the radioactive materials. So again, we need to handle this liquid waste, and also, of course, there is some spilling of the radioactive materials, and sooner or later these buildings must be decommissioned. So after the production of the nuclear fuel, now we come to the nuclear power plant. That consists of many parts. Again, just schematically, we can divide it by two parts that are called the nuclear island, that consist of the nuclear vessel itself, with the nuclear fuel, with the control rods, with the steam generators, with these pipelines, with the containment building. So all this together are called the nuclear island, and the conventional island with all the other systems, non-radioactive should be. So it is a turbine with the generator of the electricity, with all these condensers, pumps, the cooling system, etc. With the grids. So all these are conventional plants. So here it is just main parts of the nuclear power plants that are combined in nuclear island and the conventional island, with the features, with their properties, with their objectives, and the main object for us, it is of course the nuclear reactor itself. And nuclear reactors, they are very different, and there are a lot of different classification of reactors, either first of all by the spectrum of neutrons that are used in the reactors, because from these physical characteristics, all are not all, but some of the other characteristics depend. For example, if we use the thermal neutrons, so the low energy neutrons, that means that, but why it is called fast and thermal neutrons? The neutrons that are produced during the nuclear reactions, they have a very high energy, around 1 to 2 mega electron volts in average. So very high energy. But the probability of the nuclear reaction, nuclear fission reaction, is high when the neutrons have very small energy. And small energy means that the energy is close to the thermal movement of the atoms at the temperature of 300 Celsius degrees that is used in the nuclear reactors. So that means that we have to decrease the energy of neutrons from 1 mega electron volt to 0.5 or less electron volts. So it is more than 1 million times of difference in energy of the neutrons. To do this, if we are using the thermal neutrons, we need to use moderator. So the materials that decelerate the neutrons. And depending on the design of the nuclear reactors, moderator can be light water or heavy water or graphite or some other moderators. Coolant. So the coolant, it is the material that takes the thermal energy from our reactor, from the core of our reactor, and bringing to the system that transform water to the vapor, and then vapor generate electricity in the generator. So the coolant can be again either based on water, it is light water or heavy water, and these coolants we can use only in thermal reactors, yeah, because if we have water will be moderator for the neutrons, yeah, so it by physical properties water will decelerate neutrons. In fast neutron reactors we cannot use water coolant, but in fast reactors we can use either gas for cooling or liquid metals like sodium or lead for cooling and for the transfer of the heat from the core of the nuclear vessel. Also, the design of the first cooling loop can be different. It can be pressurized or boiling reactor. And then there are many other classifications, like it is industrial reactor, or it is transport reactor, it is small reactor, or industrial reactor again. It can be a basin type of the reactor or vessel type of the reactor, etc., depending on the purpose of the reactor. So there is a list of different types, not the full list of the different types of reactors. I will not go through all this list, of course. But today the most common type that we use in industrial application, industrial production of energy, it is pressurized water reactor. The VVR reactor, it is one of the type of these pressurized water reactors. Boiling water reactor, pressurized heavy water reactors, light water cooled graphite moderator reactors. So today, let's say it is only few of them are still in use. They will be no longer in the development. Gas cooled reactors, and that is, I would say, the future of the nuclear power plants. It is a liquid metal fast reactors, either the sodium metals or metal or lead metal as a coolant. So, and as I mentioned earlier, all these reactors can be classified by generation: first, second, third, and the fourth. And three main characteristics that, let's say, can be used to classify or to sort the reactors by generation. It is efficiency, and from the economical point of view, it is of course safety and the fuel efficiency. Of course, the first nuclear power plants, they were not very efficient. They produced quite a small amount of energy. I mentioned that the first nuclear power plant in Obninsk produced only 5 megawatt. So today, I think even the research reactors are more powerful than this reactor. And you can see that all these first generation reactors, they produce up to 50 megawatts of electricity. Then the second generation, it is already bigger reactors with the production from 800 to 1500 megawatts in energy. But the third generation reactors, they are improved in the fuel efficiency, and that is even maybe more important in safety. Yeah. The third generation, it is the reactors that nowadays are under construction all over the world, and they're quite safe. And we are looking for the fourth generation of the nuclear reactors with the prolonged time of operation, with the much higher efficiency, either in from economical point of view or fuel use. So higher safety, and even that is called inherent safety, or so the system with the I will try to remember the word later. So it is one of such a reactor that is under construction in Tomsk region in Seversk, that is called Brest reactor. So in Russian it is the Brest is the acronym of the fast reactor with the natural safety. So that means that if there will be any misfailure in the work of the nuclear reactor, it will stop by itself without any other operations from the people, from the staff. So with the natural safety or inherent safety. Yeah, and it will be a fast reactor with the lead coolant. So, and just to have some ideas about the size of the reactor, it is one of the example. It is VVR 1200, the main type of the reactor that nowadays Rosatom is building. So you see the man who weld the vessel of the reactor, and it is only this part of the nuclear reactor vessel. So it is very massive vessels, very huge constructions, and sooner or later, and for old reactors, it is already time to decommission these vessels, to decommission with these constructions. So you can imagine that it will be quite a lot of work, a lot of efforts to dismantle all this equipment. It's rather huge. And it is another representation of other systems. So it is a reactor vessel with the other components like pressurizer, steam generators that also will be radioactively contaminated. All these huge vessels will be decommissioned. So in this case, one of the first step will be, of course, decontamination of these facilities, either with robotic systems, some other systems, or semi-automated system, and then dismantling, and only after this the demolition of the building. So it was about different types of the reactors, about their sizes, but what with the material inside the reactor, and it is very dramatic changes in the material, because if you remember, when we today the main type of fuel, it is uranium dioxide. So that means that we put in the reactor only two elements, uranium and oxygen, as a part of fuel. Of course, there are cladding made of zirconium alloys, but inside the fuel was only two elements, uranium and oxygen. Maybe sometimes gadolinium for some applications. But during the work, during the operation in the reactor, uranium goes through the fission reactions, and fission means that uranium nucleus decompose onto different parts, and it is not only, let's say, some certain decomposition on two specific parts. It is a statistical variation of different fragments, and after operation, after work in the nuclear reactor, now inside the fuel that is called now spent nuclear fuel, there are more than 50 other elements inside these materials. And also you can easily recognize the spent nuclear fuel from the scanning electron pictures, electron microscopy pictures, because it has this like a sponge structure with a lot of holes or pores, because during the fission of uranium, a lot of gaseous or volatile products are produced, and they form the bubbles or the spores inside the structure of the ceramic uranium dioxide. So there are not only gaseous and volatile products, there are a lot of different metals that can form their own metallic phases that are called epsilon phases or epsilon precipitates. They are formed, these epsilon phases, with the noble metals like ruthenium, palladium, what else? Platinum maybe, and including molybdenum and technetium. So it was uranium dioxide. Now there are metallic drops inside the fuel. Then there are other metals, active metals like cesium, strontium, barium, that can form salts with other fission products like iodine, that can form their own oxide, cesium, barium oxide, etc. So there are a lot of different, not only elements, but also different compounds of different elements now inside the spent nuclear fuel. All these changes, they affect on the thermal conductivity, mechanical strength of the fuel, and thus, even if there are still quite a lot of uranium inside the fuel, but changes in physical properties make it impossible to use this fuel any longer. So after some time, let's say 1 year, we have to change the fuel because now it become very dangerous to use it longer, because thermal conductivity is worse, that can result in the melting of the fuel. So we have to change the fuel and put the fresh nuclear fuel in the reactor and take this spent nuclear fuel out of the reactor. And if we will see on the average composition of the fuel before and after work in the nuclear reactor, you will see that actually around 97% of the material can be still used in the reactor as a fission materials. It is uranium-238, uranium-235 that is still in the fuel, and plutonium-239 and some other isotopes that can be used as a fission materials in the fresh nuclear fuel. So there are only 3% of the products, fission products, that cannot be used anymore. So only 3% of the material we need to separate. All the rest, 97%, can use again. So that why the idea of the closing the nuclear fuel cycle, it is the reprocessing and recycle of 97% of the material again. So it should be, from economical point of view, at least from this picture, it seems that reprocessing, recycling of the nuclear fuel must have very good economical advantages. Yeah, we don't need to mine uranium; it is already here. Yeah, just take it from the reactor, recycle, and use again. But actually, all these systems to handle spent nuclear fuel, to work with this highly radioactive material, all this safety system, all this organic compounds, all these plants, they are very expensive. And nowadays, the open nuclear fuel cycle, when we dig the uranium from the land, from the earth, and use it as a fresh fuel, and the closed nuclear fuel cycle, they have approximately the same economics. So the cost is approximately the same today. Of course, there are a lot of developments that are aimed to decrease the cost of the reprocessing, including the pyrochemical reprocessing. But to be honest, today, at the moment, the prices are more or less the same. But in the case of open nuclear fuel cycle, you don't need to have a reprocessing plant. Yeah, so the price is the same, but actually the open nuclear fuel cycle is not so complicated as a closed nuclear fuel cycle. That's why not so many countries are going to the closed nuclear fuel cycle. But actually, if we will see the news, even from the United States of America, now they are thinking, and they provide quite a lot of grants funding for the reprocessing of spent nuclear fuel cycle, spent nuclear fuel. So they also think about that in the very close during the near future, the reprocessing of spent nuclear fuel will have the economical advantages. But today. So the spent nuclear fuel, again, in open nuclear fuel cycle, we can say that it is radioactive waste because we don't use it anymore. We just put it in the geological disposal repository. Or in the closed nuclear fuel cycle, for example, in Russia, from the law, then spent nuclear fuel is not a radioactive waste. It is a valuable product that can be used for extraction of uranium and plutonium. So in closed nuclear fuel cycle, even from the formal waste, from the law, spent nuclear fuel is not a radioactive waste. So what we can do with the spent nuclear fuel? What the idea today, at least the general idea. There are no details on long-lived actinides like americium, curium, neptunium, but only about the uranium and plutonium that are the major components of the spent nuclear fuel. So we have thermal nuclear reactor, and then we have a spent nuclear fuel that goes to the reprocessing plant. In thermal nuclear reactors, there is a generation of plutonium, but the isotopic composition of plutonium is not perfect. There are a lot of plutonium-239, but also some part of other isotopes, odd isotopes, not even isotopes, like plutonium-238, that cannot be used in the reactor, in thermal nuclear reactors. So in the reprocessing plant, there is a separation of uranium and plutonium. And uranium, the reprocessed uranium, goes to the fabrication of uranium dioxide fuel that can be used again in the thermal neutron reactors. So it is a reprocessed uranium, and then, okay, after working in light water reactor, it goes back to reprocessing plant. But this plutonium that is generated in thermal nuclear reactors with not perfect isotopic composition goes to the fabrication of the mixed oxide fuel. And this MOX fuel goes to the fast neutron reactor. In fast neutron reactor, due to the physical fundamentals, there is, of course, the fission of some part of plutonium, but also there is a generation of plutonium from the uranium-238, and the composition of the plutonium, isotopic composition of plutonium, is changing with the increase of good fissile plutonium. So after the fast neutron reactor, plutonium goes generates like a high fissile plutonium that now can be used also in the MOX production for the thermal nuclear reactors. So we produce the fresh nuclear fuel from the reprocessed uranium and plutonium, both for thermal nuclear reactors. It is reprocessed uranium dioxide, and it is MOX fuel with high fissile plutonium, and some MOX fuel for fast neutron reactors. So the balance, so average balance in this system, it is 2 light water reactors and one fast neutron reactor. That means that actually we don't need to have all the reactors of the generation 4, these fast neutron reactors. We need a balance between the light water reactors and the fast neutron reactors. And there is another type of reactors, the molten salt reactor, that we need by estimation, by some assessments, that we need one molten salt reactor for 10 light water reactors. So even less molten salt reactors we need. So we don't need to build all the reactors as a molten salt reactors or fast neutron reactors, just a balance between thermal reactors and fast neutron reactors. So that is called dual component nuclear energy. And as a philosophical issue, let's say that the back end of the thermal neutron reactors, now it is the initial stage for the fast neutron reactors. So it's like a, let's say, artificial ore or deposit of the plutonium for the fast neutron reactors. So it's, yeah, we can say it. To make it possible, to make possible this scheme be true, we need today much better technologies for the separation of uranium and plutonium, with the separation of the short-lived radionuclides like cesium and strontium, and for future applications, for future reactors like molten salt reactor, we need technologies to separate americium, curium, and other isotopes. What are other benefits of spent nuclear fuel reprocessing? So again, we can extract uranium and plutonium for production of the fresh nuclear fuel, but also I mentioned that the spent nuclear fuel at the moment of its generation or production, it is the most dangerous, most hazardous material on our planet. But with time, its toxicity or hazard is decreasing with time due to the decay, radioactive decay of the components. But you can see that the level of the natural uranium ore will be reached only after, let's say, 100,000 years or even longer. So quite a lot of time. Yeah, the whole history of the mankind is, or the Homo sapiens is around 100,000 years by different estimations. So, and we need to make a safe repositories for the spent nuclear fuel for this period of time. So it's very difficult. Of course, it's very expensive. But if we remove plutonium and other long-lived radionuclides like americium, neptunium, technetium, iodine, for example, and the rest will be only short-lived fission products like cesium and strontium, then this level of natural uranium ore will be reached already after 300 years. So it is 1,000 times change in the time of the hazard of the material. So that means that in this case, if we will have only the short-lived fission products, then we have to provide the safety of our repository only for 300 years, or let's say, to be sure, 1,000 years. This is already quite normal time for our facilities, especially if we make underground geological disposals. We know quite a lot of buildings that have age more than 1,000 years. So it is possible to construct safe buildings, safe repositories for this period of time. So that means that with the reprocessing of spent nuclear fuel, we not only improve economics of the nuclear energy, but also we make it much safer for our next generation of the people. So, and even if we remove long-lived radionuclides like plutonium and americium and neptunium, for example, it doesn't mean that we already exclude them from our planet. Yeah, to make them to make these long-lived radionuclides safe, to make their repository safe, we need to transform them to the short-lived radionuclides, or to make so-called transmutation. So it is a word from the Middle Ages, from the ages of the alchemistry. Transmutation means the transformation of one element to another. Yeah. And actually today we can do it with this long-lived radionuclide with the use of the fast neutron reactors. It is either the reactors that are already under operation for decades. I would say it is fast neutron reactors with the sodium cooling, or it is the new type of the reactors with the lead cooling. And one of them will be a pilot plant that is called Brest. I mentioned it already. That will be constructed, that is already under construction in Tomsk region in city of Seversk. And it is a pilot scale reactor with the energy production of 300 megawatts. So it's not a full industrial like 1000 megawatt production, but still it is a huge construction. And so the building is already at very last stages of construction. There is already a vessel that is transported to the site. So the construction is in progress at the not very last stages. The physical commissioning should be started in 2030. I think, but we will see. Maybe it will be some postponing. So this is possible today, and if we remove again long-lived radionuclides, we can convert them or transmute them to the short-lived radionuclides. And there is an example of the volume of the high level or high radioactive waste that are generated in the closed nuclear fuel cycle. So it is the volume of the waste that is generated from the spent nuclear fuel that produce the energy that is enough for 4 people, one family, in a lifetime of the 75 years with the conventional Purex process. Yeah. So after the Purex process, we have a high-level waste containing cesium, strontium, technetium, other components, and the volume of this waste will be this cylinder, a very small volume. But if we will be successful in development of this transmutation technologies, the final volume of the high radioactive waste will be like this stone in the ring, very small. It is for, again, for 4 people in 75 years. Yeah, for 75 years. Every day we generate much more conventional waste like plastic or whatever. Even this bottle has a much larger volume that we generate in one day than this for 4 people in 75 years. Of course, it is a very maybe idealistic picture, but it is the goal that we are trying to reach. How we separate all these elements from the spent nuclear fuel? The main today the main process is the liquid extraction. So it is hydrometallurgy. We dissolve the spent nuclear fuel in nitric acid solution, and then we separate all the components with the liquid extraction with organic solution. Tomorrow will be a lecture on these different processes. Again, as I mentioned already, today the main process is the Purex process, so plutonium-uranium redox extraction. It is the separation of plutonium and uranium from the aqueous nitric acid solution, from all the other 50 elements by simple extraction with the tributyl phosphate. So it is TBP, tributyl phosphate, in kerosene. So it's in hydrocarbon diluents. And then uranium and plutonium goes to the organic solution. All the rest stayed in the aqueous solution. Then we separate organic phase and wash this organic phase with aqueous solution containing some reducing agent. The purpose of this reducing agent to reduce plutonium from plutonium-4 to plutonium +3. And in this oxidation state, plutonium is not extractable, so it goes to the aqueous phase and uranium stays in organic phase and further back extracted by other techniques, by just nitric acid with small concentration. So it is a very simple scheme. Of course, it looks like a simple scheme, but actually in the plant there are a lot of different equipments with the aim to separate all the precipitates that are formed during the dissolution. With the this extraction step takes quite a lot of stages. The refining of the final plutonium and uranium also takes a lot of stages. The scheme, general scheme, is very simple, but actual technological scheme is quite complex. And today there are different new extractants that are under development to make all these processes for separation more economically efficient. Yeah, so a lot of research on this topic. And the separation of uranium and plutonium by hydrometallurgical processing generates quite a large amounts of liquid waste, liquid radioactive waste. And in the beginning of the nuclear era, it resulted in heavy contamination of the environment in both in the Soviet Union and in USA, in UK as well, in France. Of course, maybe it was not the territory of UK and France, but the territory of the seas near the Great Britain and the France. So it's quite a lot of contamination with the liquid radioactive waste of the environment. Today, of course, in Russia, at least in Russia, the release of the liquid radioactive waste is forbidden. Only in some places there is a unique disposal of liquid radioactive waste, and we will speak about it tomorrow. So, but in general, if we don't have liquid radioactive waste that must be disposed in the geological media, normally we have immobilized waste. It is either vitrified high-level waste, or it is cementitious materials that can be used for low-level and intermediate-level waste. Anyway, this solidified radioactive waste, they are placed in canisters. Canisters are placed in geological media, either very deep, like 500 meters, or subsurface geological media. But between the geological media and the canister, there is always a buffer materials which aim or goal is to prevent water penetration in the repository, or if there is a failure of the barrier materials, the sorption of the radionuclides that can be released during the dissolution or leaching of the materials. And again, what we call radioactive waste, it is the materials that, of course, contains radionuclides. There is no further use of these materials, and that is impossible in the definition, important for the definition, that the radionuclides must be at concentrations above the clearance levels that are established by the country. Yeah, so in different countries we have different clearance levels for different radionuclides. Okay, and what is the advantage, if we can say so, for radioactive waste? It is radioactive decay. Yeah, with time the radioactivity is decreasing quite fast if the half-life is short. But what is the point of this radioactive decay? That with time, even the most hazardous material on our planet, spent nuclear fuel, with time become not more hazardous than the natural uranium ore, yeah, due to the radioactive decay. So with time, even the spent nuclear fuel, even without reprocessing, after very long time, of course, will be not will have not more danger or hazard than the natural uranium ore. And for many other chemical toxic elements like chromium or mercury, you can see that they are not radioactive, yeah, they're stable, so they will possess a hazard for eternity. So we can say that radioactive waste, they are good type of waste if we are looking on the very long period of time. So again, where all these radioactive waste are formed, they are generated at all stages of nuclear fuel cycle, at all nuclear facilities. When we start to work with radioactive material, anyway, we will generate radioactive waste. And it is not only nuclear fuel cycle facilities, it is also medical application, it is research reactors, it is facilities that are used for sterilization and in food and agriculture industry. It is, of course, legacy facilities, including sites where the nuclear bomb were tested. It is naturally occurring radioactive materials, and it is, of course, some accidents at all of these facilities. So there are a lot of facilities that actually can generate radioactive waste, and these facilities will be contaminated with radioactive materials, and during decommissioning we have to first make a good survey, good measurement of the radioactive content on this facility. So again, going back to the decommissioning, decommissioning is the last stage of the life cycle of nuclear facility, but unfortunately it is not the shortest period of the life cycle of the facility. So there are three main strategies for the decommissioning. It is either the immediate dismantling, the very best option. So after the stopping of the nuclear power plant or nuclear facility in general, there is a stage for the licensing of the decommissioning activities. And then there is a preparation for the dismantling and the dismantling of the facility. So in for nuclear power plants, of course, it depends on the facility, on nuclear power plants, but in average, you can see that it will take around 20 years for this decommissioning. And it is the fastest type of the decommissioning. The deferred or delayed dismantling means that there is no techniques at the moment to dismantle all this facility immediately nowadays. So it may be due to the accidents at the facilities, for example, like Chernobyl or Fukushima accidents. We don't have technologies to work with this melted nuclear fuel material. There is no possibility to extract it, to excavate this material and remove it. So it is only a delayed possibilities, so delayed dismantling, when in the future there will be technologies to excavate these materials. Maybe it will be possible to dismantle, but today it is not possible. So if after some years it will be possible, yeah, to dismantle, then it will be done. But it takes around 50 to 60 years in this type of the decommissioning. And the exceptional way of the decommissioning is the disposal in place or entombment. So in this case, these two phases are similar to the immediate dismantling, so it will take around 20 years, and then the facility itself will be disposed on site. So then it will be operation of the repository. So we don't remove the facility completely. Now it is not a nuclear power plant, for example. Now it is a repository. In this way, for example, in this case, we can dismantle facility completely to make so-called green loan. That means that there is a natural environment, yeah, so grass without no features of the radioactive materials, nuclear facilities, but it is not always possible. Yeah. It is not always possible to completely dismantle uh, and remove the control of this territory. So you can see even from this picture that decommissioning is very complex task, takes a lot of time, a lot of finances, of course. So it's another picture of this decommission. I take it from the IAA course. And this decommissioning process must take into account a lot of different parameters. It is not only financial sources and technological factors, but it is also, of course, stakeholder communication. So it is all the people who are involved or who can be affected by this process. For example, if nuclear power plant is the only industrial object in this territory, so there are a lot of factors like social. There is socio-economic factor. If we dismantle, yeah, we decommission nuclear power plant, there is no more industrial object for the people who worked all their life in this object. So there are a lot of ethical factors, socio-economic factors, stakeholder communications to choose, to select the best strategy, the best option for the decommission. So again, it is not only technological issues and financial issues, and there are a lot of communication with the population, with the people who are living in this territory. And also that, again, nowadays, people who are working in decommission are facing a lot. It is a very bad knowledge that we have about the old objects nowadays, because not very often, but sometimes, even if there were some changes in the construction of the facility, these changes not always were written on the paper, so there is no information about these changes. And sometimes then people started to dismantle the wall, then there is some pipelines in the wall and about which they don't have any information. So the knowledge management of the objects about the object is very important for the decommissioning. It is a lot of stories from the people who are working in this field that sometimes they start to already dismantle the object, and they either found some new pipelines or some vessels that are not written in the original plan, not mentioned in the original plan, or they cannot found they cannot find the pipeline or the vessels that were in original plan. So the knowledge management is a very crucial part of the decommissioning, and we will have another lecture on this. So what about the objects that we will need to decommission in the near future? So you can see that by 2050, the estimation that it is more than 1,200 facilities that must be decommissioned till this period of time. Till this time. So it is not only nuclear power plants, but it is different objects of the nuclear fuel cycle, including reprocessing plant, including the mining facilities, and also research reactors that some of them are quite old already. So it is quite a lot of objects for the decommission. That means that the market of the decommissioning will increase with every year. And as far as the number of nuclear power plants is increasing, again, that means that after some time, the number of the objects will only increase for the decommissioning, I mean. So, and what are the technical actions for the decommissioning? It is decontamination, dismantling, and demolition. Yeah, and decontamination, again, there are plenty of different methods depending on the type of surface, type of paint on the surface, depending on the radionuclide, depending on the story of the operation in technological operation in this room. For example, was it some evaporations or some spillings, or what was the processes inside the building? Depending on these parameters, different methods can be used from the mechanical methods, when you just put some mechanical strength to the paint and take it from the wall, or it can be some electropolishing, or it can be use of the carbon dioxide polishing, or some other techniques. Again, it just list of the different methods that can be used for the decontamination. And I think on Wednesday we will have a lecture on these different types of the decontamination. There are, of course, advantages of the decontamination. First of all, we can reduce the volume of the radioactive materials. Yeah, if we have, for example, walls, and it is only a thin layer that is contaminated with radioactive materials, we can remove only this thin layer and put it in, I don't know, the 200-liter barrel, and that's it, instead of taking all this wall as a radioactive material. Yeah, so we can really significantly decrease the volume of radioactive materials for further treatment or disposal. Thus, we can decrease the cost of the decommissioning. But there are disadvantages, of course. First of all, it is the radiation doses, higher radiation doses for people. who make this decontamination. Sometimes decontamination is efficient decontamination is impossible, especially if the radionuclides penetrates deeply in the structure of the materials. That means that decontamination is useless. There will be no decrease in the volume of the material, but it will be increase in the cost of the decontamination. So before the choosing the method of the decontamination and before the choosing before the making a choice, do we need decontamination or not, there is always assessment of the advantages or disadvantages of the decontamination. So decontamination is not inevitable part of the decommissioning. It can be excluded from the decommissioning plant. And then there is dismantling of the equipment again, as far as even after decontamination, not all the radioactive materials are removed, can be removed from the equipment. Then there is a need of the special methods for dismantling that, for example, will concentrate the dust during dismantling. Yeah, if we use a saw, for example, then a lot of dust of dust is generated. We need to concentrate this dust. So there are special devices for concentration of the dust is one of the example. So for dismantling, again, it will be on Monday, next Monday, I think it will be another lecture. It's just a brief advertisement of other lectures. And the last, not last, it is one of the example of the remote dismantling. One of the company, Brock, has developed quite a series of the different robotic systems for dismantling. Just one of the example of these systems. And the last part of the decommissioning is demolition. So here, for demolition, we can use the conventional technologies. There is already no radioactive materials inside the building, and in this case there is no need for special demolition equipment. So in this case we can use the conventional types of the demolition. So as a brief conclusion, that nowadays nuclear energy is a very important source of energy. It is very sustainable. It is the one of the cleanest and one of the safest source of energy. Nuclear fuel cycle includes all the steps. It's not only nuclear power plant, it's all the steps from the mining of uranium ore to the disposal of either spent nuclear fuel or radioactive waste. And radioactive waste, they are results of any activity with the radioactive materials. Decommissioning is the final and inevitable stage of the life cycle of any nuclear facility. And we saw three main strategies: immediate dismantling, deferred dismantling, and disposal on-site entombment. And as you see, there is a big growth in the decommissioning needs in the near future. So that is all for this first introductory lecture. Thank you for your attention. If you have any questions, please ask. So thank you. If not, mhm. I think the best option is at the end of the school when we will have all the lectures from all the lecturers. Then it will be possible. I think we will make a link to the cloud, and
And I believe that it will not be done immediately upon the end of the school because our teachers are not very, say, eager to share their presentations. We'll do our best to collect as much as possible. And once done, we will send the link to the channel and then you can get all the presentations.
Okay. So now we have time for lunch.
If I'm not mistaken, we have a lunch break till 3 p.m. Correct? This check our problem, right?
Yes.
Yes. Exactly. So what we will do, we will give you these tokens that I told you before, right? And at the same time, I will ask you to sign the list of participants. This is to confirm your presence. Okay? So we will give you the tokens and we will escort you to the canteen at the main department of chemistry. The main building of chemistry department, right? We will escort you to the canteen. Have your lunch. I'd rather see that you will make back for the day. Okay, please don't be late. At 3 p.m., let's start the program. You will have your self-presentations. The PPT you sent me earlier already start, right? And they will listen here. So in fact, the list of the presentations will appear in the field that I received them from you. So please be ready anytime, okay? And so, sorry, can we leave our stuff here or should we?
Yeah.
recent years, please.
Hello everyone, my name is Omar. I'm from Egypt. I finished the specialist degree in nuclear power plant design and operation in Tomsk Polytechnic University. And I finished the master degree in last year. And now I'm going to second year of PhD in Tomsk Polytechnic University. That's all. It's enough.
On top of that, I would like to add that Omar is participating the 7th time in the International Schools on Radiochemistry. So he's nearly a team member, I would like to say. Who's else? You please, John.
Thank you. Hello. My name is John. I'm from Nigeria. I have my qualification in pharmacy, at the Bachelor of Pharmacy and also Doctor of Pharmacy from the University of Benin in Nigeria. Currently, I am a second year student of First Moscow State Medical University, named after I.M. Sessionov. There I'm studying for my master's in public health. So my aim here is actually to learn from experts. I've seen a lot of good CVs that I can learn from. So I want to, marry the health impact of radioactive substances with the environment and how we can combat that, as well as the use of radioactive nuclide in diagnosis and in therapy. Thank you so much.
Thank you. So I believe we've done. Yes. Okay, so now we have a break till 4:30. After that, we will have a virtual tour. Okay, and that will be, I believe, our last activity in the class today. Okay, have a break, please. Sure.